All right, people. So today we are going to be still talking about 6.2, but we're talking about calorimetry now. All right. So now that we know that enthalpy, um, right, our delta H, under certain conditions, under constant pressure, we knew that that was equal to the amount of heat that was flowing between the chemical reaction that we're going to study. Right. So now we got to be able to calculate this, to be able to figure out how can we get a value of delta H through experiments. How do we measure the heat of a chemical reaction? Well, the way we do that is through calorimetry. Calorimetry is well, a calorimeter. Here's an image of like a very like a this is a homemade calorimeter, but it's a good enough calorimeter for high school. Um, but what a calorimeter does, it measures the amount of heat that is released or that is absorbed from a chemical reaction. Calor, heat, right? Like caliente, heat. And then meter as in it measures that. So it measures the heat of a chemical reaction. Now, if we do this under constant pressure, well, that gives us our delta H. All right, and delta H is going to be a very important value in when we go cover thermodynamics. Okay, so the formula for that is used in calorimetry is heat is equal to the mass times something called the specific heat times the change in temperature. And I'm gonna show you these units off to the side. You get out of here. Yeah. So Q, it's the heat of the reaction, aka enthalpy, our delta H, and we measure that in joules. The mass is in grams. It's the mass of the substance that we're studying. If we're studying, yeah, it's just the mass of the substance we're studying, or the mass of the solution that we're studying. um, Heat capacity. Now, heat capacity is something you haven't heard before. Heat capacity, I think if I describe heat capacity a little bit, you'd be able to understand what it is. I want you to think of a hot summer day, a hot summer day, and um, just think of your preferences. All right, say your feet, you're barefoot outside. Would you rather be standing on metal that's been out in the sun, or would you like to be standing in a pool of water? Well, all of us, except for like a few crazy people, would prefer standing on the pool of water because it is cooler. And then the metal is going to be crazy hot. If you ever touched a railing on a hot day, oof. Or when you're going to put the seatbelt on, but then that little clip accidentally touches your neck and you're like, that that is specific heat capacities, or sorry, heat capacities in action. Water water has a very high heat capacity, and what that means is that it takes a lot of energy to raise the temperature of water, as opposed to a metal like, let's say iron. The value right here is 0.45. What that tells us, it tells us in this case, when it says specific heat, it refers to 1 gram. So right here, what this says is that we need 0.45 joules to raise 1 gram by 1 degree Celsius. So we got to put a little bit of energy in there to raise the temperature by 1 degree. Water, on the other hand, has a significantly higher heat capacity. What that means is that it needs a lot of energy. It needs a lot of energy. I thought my mic was muted. It takes a lot of energy to increase the temperature. So that's why pools take so long to get hot. That's why, like on 115-degree weather, you jump into the pool, it feels cold. Um, Now, so the higher the value of the heat capacity, the more energy it requires to get it hot. So the more resistant to a temperature change. Now, there is specific heat capacity. Specific heat capacity refers to when we're doing 1 gram, when we're looking at 1 gram of the substance. When we are looking for 1 mole, we call it molar heat capacity. And the difference is the unit, that G is going to be a mole. All right. But we're going to talk about the calorimeter a little bit more in detail. I think once we're doing some problems, you'll be able to kind of look at this and try to figure out what we're really doing. But if we break apart the portions, right? Well, how are we going to measure delta T? We're going to measure that with a thermometer. Well, how are we going to measure C? The way we're going to measure heat capacity is, well, there's already a bunch of tables that have values for that. So we're mostly going to get our heat capacity from tables like these. Or if we do all our reactions in water, we know, water's heat capacity. That's a number you have to memorize, by the way. You must. And then M is the mass. Well, how do we measure the mass? We just use a scale. And then how do we find heat? Well, we multiply all those numbers up. Okay, unless you already know the heat, then you can find something else. But let's take a look at how we do these practice problems. Okay, so let's take a read. So when 1.00 liters of a 1.00 molar barium nitrate solution at 25 degrees Celsius is mixed with 1 liter of a 1.00 molar sodium sulfate solution at 25 degrees Celsius in a calorimeter, the white solid barium sulfate forms and the temperature of the mixture increases to 28.1 degrees Celsius. So we know our final temperature and our initial temperature. So we're going to write that in already. 28.1 degrees Celsius. Remember, change is always final minus initial. So 25.0 degrees Celsius. That looks like a parentheses. I'm going to change that. I'll put the letter C. All right. Pretend I don't write ugly, so it looks nice. Assuming that the calorimeter absorbed only a negligible quantity of heat. So let's assume that there's no outside heat coming in. All right. That our little that styrofoam cup, let's pretend it actually works. The specific heat capacity of the solution, so heat capacity is C, right? So 4.18, and this is joules over C times G, degrees Celsius, times a gram. And then it didn't give us mass, but what it did give us was density. It tells us density is 1.0 grams per milliliter. And if you don't remember, density is the same thing as the mass divided by the volume. Or if you want to find mass, mass is the same thing as density times the volume. So since we want to find this, it means we're going to have to use density to figure out the mass, okay? So I'm going to leave that off to the side over here so we don't forget. That D looks a little weird. All right, all right, whatever. And it says calculate the enthalpy change. So it's telling us to find delta H. It's telling us to find delta H. But what we know is that delta H is the same thing as the heat at constant pressure. So let's go ahead and first of all, let's write a balanced chemical equation. You should always have a balanced chemical equation. All right, get out of here. So it says barium nitrate reacted with sodium sulfate. So we wrote that. They're both aqueous. How do we know that? Well, NO3 is always aqueous and Na is always aqueous. So on the products, Na was aqueous. But barium sulfate, how did we know that was a solid? They told us it's a solid, but in case you forgot, boom, there's your solubility rules. Look through them, okay? It doesn't say anything about sulfates. It says sulfide. Oh, right here. Sulfates are soluble in water except with Ba. So barium sulfate is a solid. So in reality, we don't need all of our chemical equation. In reality, we need the net ionic equation. We can get rid of this because only the important part is this right here, the barium, the sulfate, which came from this right there. So how do you get rid of this? Let's get rid of a few things. Let's clear up some stuff before we get started, okay? All right. So let's go. And we need mass. Before we can even use this equation, let's find the mass. And we said that mass is the same thing as density times the volume. So the mass is equal to, we know the density is 1.0 gram per milliliter. And then how much volume do we have? How much volume of this do we have? We have 1 liter. So in reality, right? In reality, we have a let me see. Okay, issues. Milliliters. We have milliliters here, and we have liters here. Now, you want the final solution, right? So they're telling you that we had 1 liter of this, and we have 1 liter of this. So at the end, we have a total of 2 liters. So we're going to end up multiplying by 2 liters. But the liters and the milliliters do not cancel. So what we should do first is make sure we have the appropriate units. So what we can do is we can turn 2.0 liters into milliliters. That's the same thing as 2,000 milliliters. So let's multiply by 2,000 milliliters, and then we have 2,000 grams of solution. So 2,000 grams. All right, so now that we have that, we don't need this anymore. We can go and try doing our problem. Our heat at constant pressure, of course, is equal to 2,000 grams times our heat capacity, 4.18 joules over degrees Celsius times G. And then our delta T, that's going to be a 3.1 degrees Celsius. And let's take a look at the units. Look, the degrees Celsius and the degrees Celsius cancel, the grams and the grams cancel. We're going to have joules. So this right here, let's put QP is equal to, and let's see the calculation. Calculadora. Where are you at? So 2,000 times 4.18 times 3.1, that gives us 25,916 joules. All right, that is our heat that's released. But says calculate the enthalpy change per mole of BaSO4. So what you have to do is see how much BaSO4, how many moles of it did we make? In this problem, we made 1 mole of BaSO4. So we can divide this by 1 mole because we had 1 mole. If we had made 2 moles, we'd put a 2. If we had made 3 moles, we'd put a 3. So this right here is equal to our delta H. So our delta H is, we're going to round this. What about sig figs? Should we have 3 sig figs? So 2,500 or 25,900 joules per mole is our answer. And there you have it. That is the enthalpy change. All right, so did this absorb or did this release? Since it's positive, that means this reaction absorbed this much energy. That should tell us that this got pretty darn cold. But wait, whoa. Why should I? Hold on a second. Hold on. Absorb. Final minus initial. No, this isn't right. There's something wrong. The sign should be a negative value. Oh, so let's think about it. The let's actually take a look at this value. Let's go back to our calorimeter, right? So if you mixed these two solutions inside here, right? If you mix these two solutions in here, they would release heat, and that would cause the temperature to go up. The temperature, the temperature going up tells us that this released heat. So you should always rely more on your logic and your understanding of what's happening to determine your positives and your negatives. Because remember, it's not that it means more or that it means less. What it really means is the direction of the flow of heat. Is this heat flowing away, or is it flowing into? Since the temperature goes up, temperature only goes up when heat is released. So this value here tells us that heat was released. If we want to write that in kilojoules, all you have to do is divide that by 1,000. You get 25.9 kilojoules per mole. All right, and there you have it, folks. This is how you find enthalpy through an experiment. All right, and this is going to be very, very useful in the future chapters, because what they're going to do is they're going to combine this information with the more complicated topic, and you're going to remember that. You're going to be like, oh, geez, this sucks. Sanchez warned us about this. But anyways, I'll see you guys later, and we'll cover more of these problems. Hasta luego.